So I'm Jeff Estel. I'm a Principal Customer Enterprise Architect. My friend Monroe has told me to make sure I project loud, so he's giving me a thumbs up. With me, two colleagues. I'll let them introduce.
My name is Ayan Ray. I'm a Senior Generative AI Partner Solutions Architect with AWS.
Hey, my name is Uday Thipireddy. I'm a Senior Principal Solution Architect with Elastic. Hi, everyone.
Great. So thanks, everyone, for coming and sticking around late, and I'll actually a little bit later. So today we're going to talk about building RAG applications with Elasticsearch and Amazon Bedrock. So everyone is probably familiar with Stack Overflow. It's a great site. You go on there and you find code examples and you tell people you don't. But what we're doing here in the, up till recently was you're playing kind of that keyword game where if you had an exact stack trace, no problem. You could find it, you'll find 20 topics about it. But if you're trying to find how to do something, you kind of had to, again, play the game of what keywords do I think are in that topic answer, right? I mean, you get to it and it worked, and we all did it for a long time. So then earlier this year, Stack Overflow worked with Elastic and AWS to use Elasticsearch as a vector database for them. So they embedded the questions and the answers, and so now users are able to ask their questions naturally instead of having to just pick out the individual keywords. And so they use Elastic for, the vector search and semantic search, and then to go a step further, because we're not just sending you, again, a list of topics that you have to go weed through, we want to get to the actual answer, they connect with Amazon Bedrock service to then generate the answers. And the way this works is with RAG. I'm sure most people have heard it 1,000 times, retrieval augmented generation. But you find the answers that are in Elasticsearch, that grounds the LLM, and then we send it to the Bedrock model to generate a nice answer for them. So there's really three key kind of topics or points that we're focused on these days. Just like the Stack Overflow point, is that we're after answers, not just links anymore. For decades, since Google's been around and before, really, we've all just been used to getting a pile of links, and you go, and then you have to go dig through and find the answer yourself. It's great that you got a pile of links instead of a book, but it still work. What we want to do these days is provide direct answers to cut down on the time to get the answers. We believe that RAG is a key element in every or almost every generative modern application these days. And the real reason for point two is because it's your proprietary data that powers and grounds these LLMs and really brings out the power. Now, anyone can go on the internet and go to one of the many popular LLMs out there, and they do a great job if you're just asking about general things. How do I build a fence? How do I fix my car? But if you're asking information that is only something that your company knows, or importantly, has been updated since the last time these large foundational models have been trained, this is where RAG comes into play, and this is where your private data can really power these LLMs. So much like hearing RAG everywhere, you've probably seen a lot of RAG architectures. This one is a little interesting. I haven't shown this one before. I'm sure you've seen it. But we're working with how to combine the great powers of Amazon with Elasticsearch. So in this scenario here, you have your data pipeline in AWS, and the AWS Lambda can do a lot of things, obviously, but a few of the things that it can do with data pipelines is it can enrich them, it can filter out data, and it can connect to, in this case, one of the Bedrock text models to generate embeddings for some of the log data or whatever the messages that are coming over the wire. So you can do that in flight, and then you can store all that enriched data in Elasticsearch as a vector database and as a traditional data. So then at search time, it's kind of the reverse. So Elasticsearch will help you find the documents and whatever your data is that has the answer to either it's a question or it's a query. And you can then connect back to Bedrock to find the embeddings for that query question. You can connect it back to AWS Lambda, which can also, of course, connect to Bedrock. So by placing Elasticsearch as, we've been a search engine for over a decade, and this is what drives Elasticsearch. We drive more search boxes than anyone on the internet and more applications. So we can find the documents, and then we work with, the generative great models like in Bedrock to help find the answers for you. And so as important as vector databases are, and they are extremely important, they're still only a starting point. I'm sure if you were, been on the floor downstairs, today or yesterday, you've seen many companies that are focused solely on being a vector database. And while that's important and retrieval is important, it's still just one starting point. LLMs still need to be focused and have intentional feedback. And part of this is building not just the retrieval of the vectors, but an entire search application, and we'll talk about some of the features that you need to keep in mind when you're doing that. So Elasticsearch is we call it a relevance engine these days, but it's building on top of the decade plus of development we've been doing. And so our vector database actually came out in version 7. For those of you who may not use us, thank you for coming too. But we're on version 8.16, so this is at least 3 years ago, and we introduced kind of basic support for dense vector support, doing script scoring. And then in version 8, we started with HNSW to do approximate nearest neighbor and all the new fun, fancy vector search technology that comes into play. We've done native optimizations for speedups, and Elasticsearch has been proven at scale and for security at enterprise scale and petabyte scale of data. We're focused on, again, as a search engine, relevance and retrieval. So, we believe we have the best hybrid search engine out there. Hybrid search is one of those terms that throws around where you're combining lexical search, that's that traditional keyword, text, stemming, all those things we've been doing forever, with, semantic search. We have an inference API to connect to all the, inference services that are out there today. You can connect to all the Bedrock services. But again, all the other search capabilities that we've been doing, things like geospatial, date manipulations, things like that are things that we're really great at. And we want to make sure we're focused on having great default choices to make it easy for people to get started these days. There's lots of choices out there, and so it's easy to get bogged down. So we provide things like ELSER. ELSER is our Elastic Learn Sparse Encode. The R is at the end, naming's hard. No. And this is our sparse embedding model. So sparse embedding model, similar to a dense vector model, which you probably use or are familiar with. ELSER starts as a BERT model, we train it, but then it kind of forks off and we do some late interaction scoring and we output tokens and weights. If you're interested more in that, you can come downstairs and we'll talk more about it. But we want to make it easy for you. It's a model that we train, so you can one-click install it and get up and running. And then we have things like Playground, which you've probably heard of, but its ability to test out query methodologies and prompting and things like that before you get out into production. So we've been focused on speed, scale, and efficiency in the last couple of years, more so than ever. We've been able to improve things up to 60% reduction in latency, and so Elasticsearch is built on top of Apache Lucene. It's a individual search library, and we build on that to bring scale and redundancy and lots of other fun things. And so we're committed to committing back to Lucene. So we work with Lucene and we work on what our customers need to bring all these optimizations to it. So we do things like the latency reduction when we're searching vectors. We do accelerated graph. So graph is when you're searching KNN. There's a hierarchical navigable small worlds graph, HNSW. You may have heard that algorithm. So we can explore multiple graphs at once. We can exit the graph when we find the minimally competitive candidate early, and so we save time on that. When you're searching, we can speed up by doing things when you're doing faster throughput. So we optimize for things like SIMD instructions. This is being able to parallelize at the CPU layer. We do things to reduce the memory. The fun thing about dense vector search is it works really well, but to be super fast, millisecond response times, we need to cache that into memory, and that just happens to be the most pricey of the components you put into a cluster. So we can do things like quantization, which dramatically reduce the size of vectors and in turn reduce the amount of RAM that you have to pay for. So a little bit of timeline, I kind of touched on some of this, but back in 2017, we had support for native vector search, both for on-prem and our cloud customers. Again, by contributing back to Lucene and integrating it natively within the stack, we don't just, it's not just a bolted on component that makes separate API calls. We're able to do speed ups from 7 to 290%, really depending on what you're doing. This year we've been focused again on making things faster and more efficient, which in turn makes it less expensive for your company to run. Doing things quantizing all the way down to the bit vector, which we'll talk about. And then we have a lot more planned for the coming year. Elasticsearch 9 is coming next year, and that'll be built on top of Lucene 10. So a lot of fun features coming out. Turn left. So this is my favorite slide. Because it's my favorite named feature. So this search engineer, Ben Trent, he worked on this and he came up with it. So I do a lot of barbecuing. Maybe the beard gave it away, but years ago I built like a drum smoker out of a 55-gallon drum. I had to drive out and get it. I smoked a turkey last week for Thanksgiving. If they'll let me next year, I'm going to have a breakout session on barbecuing. So I was really excited when I get to now say BBQ and barbecue 1,000 times a year and get paid for it. And what this does is really, it's a huge improvement because we take a full float vector and we quantize it down to a bit. And this provides up to 95% reduction in memory. And so like any kind of compression, you're going to lose some fidelity. But because of the way this works and some fancy search technologies, we can actually, at query time, we can oversample. We use some of the vectors that we store. So when we quantize, we still store the full-size vector. So we can oversample and do a rescoring. And by doing this, we pretty much maintain the full retrieval accuracy that you would get as a full-size vector. So for a long time, people would come and say, we have hundreds of millions or billions of vectors. And we could do it, but it was a lot of RAM. Now it's a huge improvement in speed and accuracy. We'll talk about some of the new things that we've been working on as far as generative AI applications work. So we have the Inference API, which is a simplified interface now to connect to services like AWS Bedrock. We use these also internally. So for our Elastic-Learn sparse encoder model, the ELSER model, you create an inference endpoint. And you can then do things like text embedding, text completion, re-rankings on there. We'll talk about re-ranking in a second. And so to get it up and running, all you do is make a JSON call. And in this case, we're creating a text embedding endpoint to Amazon's Titan model, and we're naming it at the end of the URL bedrock-embedding. So you do this once, and then you have it connected. And the great thing about that then is that you can use it at ingest time. You can use it with our new sparse text field, which I'll talk about in a second. But it also, in general, just creates a new endpoint. So you can create this endpoint, have it secured, and then if people are, with our RBAC and everything, developers or applications that are allowed to, authenticate to your cluster and to this API are allowed to use it too. So kind of integrating all these services together. And another thing we came out with just recently, actually I think it just came out this week, is semantic re-ranking. There's a little thing. So semantic re-ranking, if you're not familiar with it, is taking the results from a first stage retrieval, or whatever your first search is, and then re-ranking them, resorting them based on the semantics of your question. So what does the question mean, or what was the query? So it's very much like doing first stage when you're querying with vector search or semantic search. The difference, though, is that you can use it just without having your massive data set generating embeddings. So it works perfectly fine and well with vector search. So you can do a first stage vector search using one model that's really good at retrieval. You can have a specially tuned model for re-ranking, and they can work together. But you can also use it with lexical search. So you could have a lexical search look for a specific keyword or a phrase, and then you get a wide sample. You pass that to the re-ranking model, and then you can semantically rank based on like the natural question. So you're able to do this together. Elastic just released our re-ranker model, Elastic Re-rank. It's in serverless. Serverless just went GA on Monday, so it's great. So if you're interested in trying that out, you can go check it. You just make one of the API calls in there. We'll automatically download it and deploy it for you in the cluster, and then you can try it out. It'll be coming to the rest of the stack very soon. Another feature we have is learning to rank. So learning to rank really unlocks your own data as an algorithm. So it gets relevancy based on your own data. And the way it works, there's another one. Come back to that in a sec. The way it works at a high level is you have a judgment list based on your data and your user questions and interactions. And then you train a XGBoost model to based on that information. And so it's really creating a custom model based on your own data and your own user interactions. And then that model gets loaded into Elastic. So then you use a model that's created on your data to help improve retrieval in the Elasticsearch level. And I'll go back one. Just like the re-ranking stage or re-ranking model, it works as part of a multi-stage. So you can put all these different functionalities together to get really the best of all the individual features you need for your stack, for your application. So we're going to talk about semantic text. So semantic text is our new field type that we came out with recently. So for a long time, when you would want to create a semantic application or generate embeddings for your data that may be going to a RAG application, maybe you're just keeping them as vector search, it was a lot to get up and running. So you would have to pick a model that you wanted to use. There's a lot out there, an embedding model. You'd have to create it. You'd have to create the index, create specific mappings. Within the dense vector mapping itself, there's a whole bunch of parameters that some people understand, some people don't, some people pretend to. And then you also have to go and deal with chunking. So chunking, for those who aren't unfamiliar, is these models, these embedding models have what they call a context window. They're usually 512 tokens. So essentially, like if my head can hold 512 tokens, if I give it a full book or a full page of text, it's only going to hold a little bit, and then everything else gets dropped off. So you have to chunk it or break it up. So you have to have a chunking strategy, and you could do that outside in whatever software you like, and on and on. So it's a pain. So while there are still cases where you're going to get into the weeds, there's always a corner case where you're going to fine-tune everything. We still give you all that ability, but we really want to make it easy for most people to get up and running with semantic search. And the way we do this is with our semantic text field type. So we talked about the inference endpoint earlier. So you create an inference endpoint that's connected to our ELSER model. We can do that in serverless now. ELSER is deployed automatically for you. That endpoint's already up and running. So if you're using serverless, you don't even have to do that first step. You can then just create an index, and all you would have to do is create the one field that's a semantic text field and give it the inference ID and tell it that it's a semantic text field. And so as part of that, then automatically what we'll do is we'll take care of the chunking for you, we'll take care of embedding, and then we store all that for you. And then what's great is you only had to keep track of the model the one time you created a field. So any other developers who are sending data to that, that index and that field, they don't have to know or keep track of which model you're using. At query time, there's lots of people searching, probably a lot more than are sending data, right? So they don't have to know which model, because when you're doing queries against vectors, sparse or dense, you have to run the query through the same embedding model. So you have to keep track of them. Otherwise, it doesn't make sense. It doesn't work too well. So we'll try to take care of all this for you and make it, again, that easy onboarding, easy getting started. And that's where I reinvent. It's key to point out that this works perfectly well with Bedrock and is the inference API. So we show that you can connect to the Titan model. You can connect to any of the Bedrock embedding models are on there, so you can use those embedding models right in semantic text with it. You don't have to use ELSER. We like it because we made it, but you're free to use whichever one you want. So another feature that we kind of talk about when we're trying to help people understand the full breadth of applications they can build is hybrid search. So certainly I get paid to talk about vector search and semantic search all the time. Everyone on stage does. But it's key to point out that traditional lexical search is far from dead. Keyword search is still really important. If you know the term, the phrase you're looking for, lexical search is faster and more accurate. If you're looking for a part number, that part number has no semantic meaning probably, so you're going to use lexical search. If you're searching for date ranges, if you're doing geospatial, all that stuff is traditional search that we've been tuning and improving for over a decade. But there are cases where it makes sense to do both. So one scenario, if you're looking for a specific part number, but then you want to ask the question, how do I use this part to do whatever, you can combine it with what we call hybrid search using RRF. RRF is reciprocal rank fusion. It uses this little formula over here. And the way we do it in Elastic is we fire two parallel queries at the same time, And then we use this little formula to take the two sets and rank them together. So ideally, you get the best of both results sets for you. And there's a couple parameters, but usually it works pretty well out of the box if it's going to work for you. So we want to touch on geospatial. I mentioned it a little bit as one of the things we've been doing for a long time. So way back in the very beginning days, we started doing geospatial with points and shapes. We added geo-analysis aggregations and added geo at scale for improving these encodings and the way they can be improved and stored efficiently and searched. We use GIS and map analytics, and the GIS and map analytics are used by some of the largest mapping geo companies in the world. Vector tiles came out 2 years ago, and this makes it even more efficient to not only search, but to store the data and search for it. And then we're not really going to touch on it today, but there's other sessions. ESQL is our new query language. It's a SQL-like syntax, and it allows you to pipe queries together similar, to SQL queries. And this works well with geo. So one of the quick examples here is, we're filtering documents that fall inside the geometry definition for, pretty sure that's Manhattan. Elasticsearch supports filtering by bounding box in the center radius and polygon in the geoshapes. So in this clip, what we're seeing is we're drawing a box around it, but then behind the scenes, we're running this query to find all the aggregation, to find all the dots that we're looking for the aggregated features. And the next geospatial analysis is aggregating documents based on their location in the categories. So we can not only draw boxes around, say, this is 311 call center data. So we can add this layer on and find, the number of calls. That's pretty easy. But what we want to do is add in other data points. So for all the calls within there, what are the top 3 things that people are calling 311 about? Or what's the average time spent on a call with 311 within that? And I'm sure they differ. So you're able to use all this data together. And part of working with maps is making them easy for people to understand and get information out of quickly. And so we have a lot of data-driven styling that we can use. So based on the size, the width, the color, all that is driven by the data underneath. And it really makes it easy to understand really complex data maps by the color or the shape or the size of things. So I mentioned quantization and barbecue earlier. But we do have other quantization techniques available. So int8, int4, bit. By default, if you send us float vectors and you don't do anything, we're going to quantize those down to int8. It gives you about 75% reduction in the required memory. And what we found is it's only a tiny bit reduction in recall, which actually you can overcome if you increase k, that's the number of candidates, if it's, say you have a k of 10, you can increase it to 12 or 15, just a little bit, and you'll overcome any reduction in relevancy. And I talked about ELSER a few times, but just to reiterate that ELSER is a model that we trained and we provide out of the box. We host it up in the cloud somewhere, and if with one click or one API call, it automatically downloads to your cluster and gets up and running so you can deploy it where you're running your cluster. Playground is, again, our tool for you to test out your RAG application before you actually go put it in your own application. It allows you to generate queries. So this box on the right is the query builder. So you can toggle on and off different fields. And what's cool is you don't have to know how to write this JSON query of retrievers. If you do, it's fun. But as you toggle them on and off, it'll build the retrieval query for you. So if you only have semantic fields selected, it's just going to do a semantic query. If you toggle on only lexical fields, like only keyword fields, it's only going to be keyword. But if you toggle both, it makes an RRF retriever like is up on the screen. So that's a nice little shortcut too. If you want to put a bunch of fields in there and grab the query, I do that just when I'm lazy. And it works well. So you can also then, of course, the data you're doing there, it calls out to the LLM. You can connect to Bedrock and get the answer back. And one thing important, so years ago I used to work in operations, and so always important to remember that while we're really focused and everyone talks about the models that you use and the accuracy, and are they hallucinating, and are they giving away free things that you're not supposed to give away? These are still applications at the end of the day, and they run somewhere, and they connect to stuff, and they cost a lot of money oftentimes, sometimes. So you want to observe these. So we work with Amazon and AWS, all the services that AWS collects for running on their cloud, and we can observe those. So we can observe them with a custom dashboard like this. So this is the Amazon Bedrock one, and you can customize this to fit, your particular deployment needs. You can use the observability UI that's built as one of our solutions to monitor that. Our observability UI and interface and all the data also has an AI assistant. So again, when I used to work in operations, if something went wrong, it was sifting through logs, hopping on VMs, it was a mess. Today, you can just ask, the AI, why is this service slowing down? And we will do the RAG approach for you automatically. It's just because it's observability data doesn't mean RAG doesn't work, right? We will automatically, behind the scenes, search for relevant observability data, be it logs, metrics, APM, traces, cloud posture, security, all that fun stuff. Package it up, and then we'll connect to the LLM and say the user is asking about why this service is, and then it'll generate an answer, and they can talk back and forth. Two more things, and then I'm going to hand it over. Elasticsearch is a search engine that's been around for a long time, and vector databases, all of them can store and search vectors. I hope that's kind of the point. Some of them also generate vector embeddings, but rarely are you only using a vector database in isolation from itself. Especially if you're talking to us, you're probably building a search application, and you want to be able to bring in all the other features that an enterprise level, search application can bring. So things like document level security, you can secure it all the way down to the document. You can secure it down to the field if you want. We have, scale on cloud, on-prem. We can scale across data centers. We can do replication, hybrid search, and aggregation. So all the other features that I'm not going to sit there and read all those are things you want to keep in mind and things that we've been doing for over a decade. And we continue to rapidly evolve. Again, I touched on most of the yellow things on the screen today. These are things that we implemented in the last year and a half or 2 years, and most of these actually all, except for the top one, the bottom kind of curved on there, we've all done in the last 6 months. So we're rapidly evolving, and our engineers are working really hard. But of course, it's not over. So very soon, I'm not allowed to give dates. Our Elastic Inference Service will be online and available. It's going to be an inference service that works with us, so you can run ELSER on GPUs. But of course, it'll work as part of an inference API ecosystem. So you can use us for that. You can still connect to Bedrock, and you can use all this together in ecosystem. AutoOps is our automatic kind of SRE for running and managing Elasticsearch itself. So if you're observing how Elasticsearch works, if you're having issues or anything, AutoOps is kind of that intelligent, automatic SRE that sits there and never complains of getting up at 2 a.m. like I used to. And again, I mentioned DSQL a little bit. It started out as security and then moved into observability, and now search is getting involved. So all the other pipe query capabilities, you'll soon be able to do that all with semantic search and vector search and using inferences and everything. And the very last thing before handing it over is I do want to talk real quickly about one other customer reference. So HSC is a large home shopping e-commerce company in Germany. And so they had a black box search solution that worked well for a little bit, but it was very narrowly focused. If you're within the lanes, perfect. But as soon as they wanted to start tweaking and tuning the search results and some of the other capabilities to meet what their customers were asking for, they were having trouble. So they worked with Elastic and AWS to combine and build a modern search application that allowed them to build on natural language and embedding, and then you can see some of the impact at the end on that slide. 4% rise in click-through rates, 8% increase in satisfaction, and 42% reduction in the employee hours spent on software maintenance, which is a lot. So I have talked for about 30 minutes, and thank you for listening. I'm going to hand it over.
Oh, sorry. So hey everyone, as I introduce myself, I'm a generative AI partner solutions architect. So as a solutions architect, I work with a lot of partners and many customers. And there are few common questions that they always ask me. First of all, they ask me, Ayan, there are so many foundation models to choose from. How do I choose a model that best fits my use case? Then they ask me, how can I build and deploy my generative AI applications quickly using foundation models? And last, but the most common question, specifically from larger enterprises, is how can I keep my data private and secure while building generative AI applications? And the answer to all of the questions is Amazon Bedrock, which is a fully managed service from AWS that provides you with a choice of high-performing foundation models from leading AI companies, along with a broad set of other capabilities that helps you to build, and more importantly, to scale your generative AI applications. With Amazon Bedrock, you can easily experiment with the foundation model of your choice, customize them privately and securely using RAG, fine-tuning, or continued pre-training, and you can create managed agents for performing complex workflows like booking a ticket, managing inventory, and many more. And Amazon Bedrock is serverless. That means you can do all of what I just mentioned without having to do the undifferentiated heavy lifting of maintaining and managing your own infrastructure. Now, generative AI as a field is moving extremely fast. You've heard about the announcements that happen at re:Invent. So practically, a new innovation is happening almost every day. Now, if you're building a product, it might so happen that by the time you complete your development and you're ready to move to production, a faster, cheaper, or a better model is available. Now, what do you do in such a situation? Two options. Number one, you delay your product feature release, but that also means losing out on a competitive advantage. Then you are left with option two, which is to either compromise on your user experience or on your margin. So if you think about it, the best tool that you can have today is the one that lets you use the best foundation model that is available today and also lets you quickly embrace what is coming up tomorrow. In Amazon Bedrock, you can get foundation models from leading AI companies like Anthropic, Meta, Mistral, Cohere, AI381 Labs, and we all Stability AI, and we also have our Amazon Titan and now Nova models. I'd like to double-click on the privacy and security aspect of it because that has always been a priority zero for us. First of all, we do not use any of the customer's data to train the original foundation models, period. Even when we are fine-tuning a foundation model, we create a private copy of the model, put it in a secured container that is accessible only and only to you. Your data is secured both at rest and in transit, and you can privately access a foundation model in Amazon Bedrock from your own virtual private cloud without traversing the public internet, and that is possible through its integration with AWS Private Link. It is compliant with GDPR, ISO, SOC, and many other regulatory standards. Consumption options. The default is on demand, where you pay as you go based on your LLM token count usage. Great way to get started for POCs, prototyping, and even for smaller workloads with relaxed requirements of throughput and latency. But as you move to production and as your usage grows, you might want to reserve sufficient throughput for your application. That is when provisioned throughput option in Amazon Bedrock is a great way to reserve sufficient throughput in order to meet your application's performance requirements. We also have batch inference API where the cost is 50% of the on-demand APIs. And this is a great way for running inferences at scale, for running evaluations, offline processing, or for experimentations. Amazon Bedrock Guardrails helps you to implement safeguards for your application, which are tailored to your application and also helps you to meet your responsible AI requirements. You can define topics using short natural language descriptions, the topics that you want your generative application to avoid. And you can also specify thresholds to arrive to avoid harmful content at varying degrees. Converse API for Amazon Bedrock provides you with an unified and consistent input and output or request and response structure, irrespective of the foundation model that you are using in Amazon Bedrock. It also supports basic prompt translation in terms of user, system, and assistant prompt. And it also supports native function calling for Anthropic, Cohere, Mistral. Jeff told us about RAG. A critical component of the RAG is to generate and store vector embeddings. And comparing embeddings improves the relevance and the contextual responses. Along with the image generation models, text generation models, multimodal models, we also have embedding model in Amazon Bedrock. One such model is Amazon Titan text embedding model. You can generate the embeddings using Amazon Titan embedding model and store it in Elasticsearch. Elastic can accommodate vector dimensions of 4096 dimensions. Titan text embedding generates dimensions of 1536, so you can easily store that in Elasticsearch. You can do that using the native AWS and Elasticsearch APIs, or you can use any of the popular frameworks like LangChain and Llama Index, both of which have built-in integrations with both Amazon Bedrock and Elasticsearch. Or you can use the Open Inference API, which Jeff demonstrated, for a more native and out-of-the-box experience. These are some of the code samples built using Amazon Bedrock and Elasticsearch. I'd also like to cover about a customer who is using RAG underneath, but they are the customers of the Elastic Security solution, which is built on top of Elasticsearch. They leverage Elastic Security solution in conjunction with Amazon Bedrock, and they have gone on code to say that it has helped Proficio to improve their productivity by 34%, and they're predicting $1 million savings over 3 years. With that, I'll hand it over to Uday for a demo.
This demo, I know Jeff covered about all this inference APIs and also RRF and other things, and Ayan covered all the Bedrock models, right? So today I'm going to show how you can consume Elastic, like, I'll just get started. So you can see that you can start the trial from directly from here. There's a direct trial. You will get 14 days. 14 days you can start a trial, or you can come to Amazon Marketplace and then you can start a trial here. You will get a 7 days trial and free trial, and you can deploy Elasticsearch there and test your solutions and embeddings and things like that. So you can see that how you deploy is you can try for free, and you can actually request a private offer if you like it. So deployment is pretty easy, and then you don't have to. Sorry about the technical issue. It went back. I think it's there. Sorry. So you can. Yeah, sorry, I'll cover from this here. Sorry about that. Yeah, like I said, the marketplace offering, you can go to marketplace, you can discover Elastic from the marketplace. You just try the free trial. It's 7 days. We'll give unlimited storage, and also we'll give the compute and machine learning nodes. The deployment is pretty easy, and you can come here and see. You can request a private offer, or you can use a CloudFormation script. You don't have to learn any programming knowledge. CloudFormation is automatically deploys your Elastic cluster from your console. So you just have to click the launch template. This template is easy, and it deploys. It uses the Elastic APIs, and that will deploy your Elastic cluster data nodes and machine learning nodes and everything. That's all seamless. All you have to give is Elasticsearch, the region where you want to deploy, the name of the cluster and a deployment name. So that will deploy your Elastic cluster. We support more than 23 regions, so including we have 2 GovCloud regions. So all you have to acknowledge and deploy from here, and that's one option. Once you deploy Elastic cluster, so you will come to this particular console, and you'll see that I have a hosted version. And as Jeff mentioned, we recently launched a serverless offering. So you can create a serverless project, and we offer all 3 solutions: Elasticsearch, observability, and security. So in this demo, we are showing the Elasticsearch. So I'm clicking Elasticsearch. Here you can give the name of the project. The project name is just you're identifying the deployment. You can choose the region here and deploy the project. So once you deploy the project, you'll come here. I'm not deploying, it takes some time, so I already deployed for you. So once you are here, you can come and create an index, and then you can play around with all the features like dev tools. You already know the same experience. Serverless, we are giving a same experience. There's nothing new. You can come here and, in dev tools, you can create an index, you can load some documents, and you can search the documents. It's pretty easy, and we created it for you. And then you look at the discover and all the documents, you can check it from there. So it's pretty easy to operate. And Jeff mentioned that we have a playground, and also you have all the help, getting started help here. You can see all the Java clients and API keys. You can get more help from here, and you can easily onboard and deploy all these clients with the code samples. With that, I'll start the playground demo. It's easy to start. I already created a demo here. The playground, if you click on the playground, you'll see this. And then Jeff mentioned that we have the API with the Amazon Bedrock. All you have to give the access key, and this access key and secret key, and also the region. And once you give that, you just enter the documents, whatever you want to test. In this case, I'm inserting some of the geospatial data. So just to show you how it will work, and then I'm creating the fields for that, and I'm putting some documents just to show some examples how we can create a vector embeddings. So I loaded some data, and if you look at that, right, I added 2 models. You can actually add a Bedrock you just have to connect and then give the API key and secret key, and then that will give you the Claude 3 and also 2 models. And here I'm adding a data also, and that data is like just to give the context. Like if you add a data Elasticsearch index name there, that knows the context, then it will help avoid the hallucinations. So without a data, it can predict. And I'm giving the question like, find me a townhouse near to Cupertino, California, and that will find the homes near to 5 miles, and that has a swimming pool. So it's easy, and sorry, it's just the timeout error getting, okay, sorry, that because of I'm using the free version of the Claude, so that's why I'm retrying that. Give me 1 second. So that will give the results here, and you can see that results based on the context provided. So it found some of the nearest townhomes, and that will give all each of the results here that has a swimming pool, and then also the close to 5 miles that will find all the townhomes. And also we have this documents. You can see where the context it got it from, and then also it will give the relevance score. So you can check the top relevance score, all the documents with the relevance. It will give only the related to that. And then also the query you can see as that particular column. I'm creating the vector embeddings, and the field also it's giving there. So you can check the Bedrock embedding model which field I'm searching for. And that's about my demo, and I'll give back to Ian to cover the geospatial demo. And the documentation is there, so you can check if you have any questions there. So, thank you.
Yeah. So before I jump onto the demo, I'll reiterate what Uday just mentioned. So there are a number of use cases in the enterprises where semantic search alone is not sufficient. Think about real estate. Like you want to search like you want to design a conversational AI assistant to help potential buyers. That's exactly what we are going to demo using Elastic and Bedrock. Now, the query that Uday mentioned, find me townhomes within 10 miles of Cupertino, California, and show me properties that has maybe a spa, sauna, swimming pool, private backyard. Now, let's dissect this query. First of all, it is asking for townhomes. And Jeff mentioned, if you're very clear about what you want, keyword search shines in that scenario. The user doesn't want a single family residence or condos. He wants townhomes. That is where keyword search really shines. The user has also mentioned about, okay, tell me about private backyard, show me properties with a private backyard, spa or sauna. This is where it is important to understand the intent of the user. That means the user is interested in private backyard, spa or sauna, and the user might be interested in a private patio or a gym, or a clubhouse or a sauna. And then the user is also saying, this is where semantic search shines. Semantic search helps to understand the intent behind the query. So it will show you properties with a private backyard, spa, sauna, but it will also show you properties with a private patio, clubhouse, etc. The third thing, it also mentions, show me properties within 10 miles of Cupertino, California. Anyone from San Francisco Bay Area over here? Cool, quite a few. So if you're familiar with the San Francisco Bay Area geography, Apple campus is in Cupertino, California, or say I just search 10 miles from Apple campus, it is in Cupertino, California. So 10 miles from there will mean some areas of Cupertino, California, but might also mean neighboring areas of Santa Clara or Sunnyvale. Now, it will be difficult for semantic search alone to figure out which properties within neighboring areas of Sunnyvale and Santa Clara falls within 10 miles from the Apple campus. That is where we need a combination of all three. We need semantic retrieval, we need keyword retrieval, and we need geospatial retrieval. The demo is all about that. It's a demo conversational AI assistant for real estate customers, and we'll just see that on screen. This is the architecture behind it, and this is the query that makes it happen, similar to what Uday demonstrated. Take a close look at the prompt. Find townhomes within 10 miles of Apple Park in California. I'm looking for a private balcony, a spa or sauna, along with clubhouse facilities. An outdoor pool is even great. However, I want HOA fees per year not to exceed 10K. So first of all, what it does is it does something called named entity recognition. It identifies the corresponding entities, like what is the property type, what is the address, what is the property features. Then it geocodes. It transforms the address into lat-long using Amazon Location Services. And the response that you are seeing is a result of a hybrid, geospatial hybrid query that combines geospatial filter with keyword search, with semantic search. Keyword and semantic search is combined using reciprocal rank fusion. And it does that, Elasticsearch does that in a very performant manner. As Jeff mentioned, scalar quantization is enabled by default. So you get the responses fast doing so. So here you can see that all the properties have HOA less than whatever was mentioned. It has properties with spa sauna, but it also has properties with barbecue area. So that's exactly what I wanted to demonstrate. These are the properties. As you can see, it also fetches properties from neighboring areas of Sunnyvale and Santa Clara, along with the properties in Cupertino. And that has been made possible because of Elasticsearch's robust geospatial retrieval capabilities. With that, I'd like to thank everyone for joining such late in this session. We are sitting between you and the cocktails. So thank you. Thank you for joining once again.